Today's video is going to look at two topics. The first being a continuation of our study of exponents. And today we're going to look at something known as square roots. So before we get right into that, I just want to review with students that when we say something is being squared, we simply mean, in this case, that the number 2 squared, we have 2 2's being multiplied. And when we say 3 squared, we mean we have 2 3's being multiplied. Similarly, when we have 6 squared, we have 2 6's being multiplied. And so students will become very good at memorizing these pairs. We have 2 squared equaling 4, 3 squared equaling 9, 6 squared equaling 36, and so on. These answers that we're listing are known as perfect squares. I want to take you away from that for one moment and just have you envision that, picture that in your head, that if we were looking at a shape, in this case, I'm just sketching a freehand, a square. And so what do we know about squares? We know that squares are the same length on all 4 sides. And so in this one, I've drawn 1, 2 units. We could say those were centimeters. We could say those were meters. It doesn't really matter. And along the bottom here, the width of it is also illustrated to show us 2 centimeters. Now, as you can see, inside of the shape, we have 1, 2, 3, 4 centimeters. And we know that as area, the surface area, how much space is taken by that 2-dimensional shape, 4 centimeters squared. You'll notice the pattern. That was the same answer we got here. And students will recognize that as the area of that shape being the length times the width. Again, from this example of 3 squared, if we had a square that was 3 units on one side and 3 units on the other side, that would mean it was 3 units all the way around, if it's going to be a true square. And if we draw the interior, the inside of this shape, you will see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares inside, as is the same as we got over here. What I want to remind students about today is to show them that we can take that answer, the root, the square root of 4, and know that the answer is 2, the opposite that we started with. The root of 9, what 2 numbers that are identical multiply together to give you 9? The answer is 3. And similarly, if I said, what is the root of the square root of 36? We would think, what are 2 numbers that are identical that multiply together and give us 36? And the answer in this case would be 6. And so we could continue with this pattern. Here are some more familiar ones in our friendly numbers. The root of 25, what 2 numbers, when multiplied, and those numbers are the same, will give us 25, and the answer is 5. Again, what 2 numbers would multiply and give us a root of 100? We would get the answer is 10. And we could check that out just to see if we were right by drawing 10 squares down and 10 squares across. And then we would take this shape and we would divide it like a grid, like we did similarly in these. And if we counted them all up, we would in fact find that we had 100 squares there. So that's the first part of our video lesson today that students are going to start out with in their booklets. And the second part that I wanted to just briefly cover is the use of two different terms. And these are going to be added to our math dictionaries. The first term is known as prime, and the second term we pronounce composite. And it refers to types of numbers. So prime numbers, students are going to memorize, simply means that if you had to have two factors, two numbers multiplied together to give you an answer, the only two numbers that you would be able to come up with if you're going to call something a prime number is the number itself times the number 1. Composite numbers are different than prime numbers because composite numbers allow us to pick two numbers that are not one of them being the number 1. When you multiply these two numbers together, these two factors, you end up getting a composite number and didn't have to actually use the number as one of the factors. So I'm going to give you a couple of examples just to illustrate this new vocabulary. And the first one I want to list is some prime numbers that I know when I do my multiplication factors. I can't think of any numbers that will give me the number other than the number 1. So the very first one is in fact the number 1 because the only way to get the number 1 is to multiply 1 by itself. Again, the number 2, the only way to get the number 2 is to multiply 1 by the number 2 itself. 3 is also a prime number because it follows that same pattern. You have to multiply the number by 1 in order to get the answer. Now the number 4 is in fact not a prime number. Yes, I could get it by multiplying 1 times 4, but many students will also recognize that you can get the answer 4 by multiplying 2 times 2. So this one is not a prime number, and in fact is a composite number because we were able to come up with at least 2 factors that will multiply and give us the answer. So we can go on with some prime numbers. 5 is a prime number because 1 times 5. 6, yes, 6 times 1, but there are other ways to get the number 6. Easily, students will recognize that you can get the number 6 by multiplying 2 times 3, which is the same as 3 times 2. So it, again, is not a prime number. It is a composite number. The number 7 can only be reached by multiplying 1 times 7. And you're starting to notice that there are some patterns here. So the number 8 can be multiplied by 8 times 1, but there are other factors that will produce the number 8. Pause for a moment and think if you can think of 2 numbers that can multiply to give you 8. And many students will readily recognize that you can multiply 4 times 2 or 2 times 4 to get that number, and therefore the number 8 is not prime, but is in fact another known composite number. Students are going to be asked to pick up a booklet, 1.3, and we're going to start by reviewing our lesson on square and square roots. There are 3 sheets to do so, and then it's going to start to look at using prime numbers to make something called a factor tree. So I'm going to do one such example so that you are not lost when it's time to work on your own. But I'm going to leave our definitions or examples up here of prime and composite numbers because it will assist some students when they have to go on and do more. So the first number that I'm going to write up here is the number 21. The question would be done, there would be nothing to write, if we could not come up with any numbers other than the number times 1, because then it would be a prime number. A factor tree is used when you know there are composite numbers that can be multiplied together to give you the answer. So we're going to try this, and I want to show you this one because you'll see that it doesn't matter how you start out, you will end up with the same answer. So some people will say, oh, I know that the numbers 3 and 7, when multiplied, give me 21. If either of the numbers, or any of the numbers, can be broken down further because you can think of ways to multiply and get that answer, then you must break it down further. In this case, both 3 and 7 are prime numbers, so the question is finished. If I change this and put the number 20, there are several ways that students could get the number 20. Yes, 20 by 1, but you could also do 10 times 2, and students would have to break the 10 down again because in order to get 10, you could also do 5 times 2. And so what you see is we have 3 numbers, all of them being prime because they cannot be broken down anymore. And if we multiply 5 times 2, 10, times 2, 20, we get the number we started with. Going over here, if I had started out by picking different numbers, as in 5 and 4, you will see this pattern develop. And again, although we didn't start out with the two same numbers, we're going to end up with the same answer because we broke the 4 down further by doing 2 times 2.